A capacitor multiplier circuit is shown here that is voltage controlled via Vcontrol that is applied at this point to control the voltage between the gate and source of this JFET with, say, this is Junction Field Effect Transistor, N-channel. And we have, as a result, we want to show that this circuit works as a capacitor multiplier, in which when we look into this terminal and between that terminal and ground, effectively we observe, and when we measure the input impedance or Z equivalent, that Z equivalent or input impedance feels as if there is an equivalent cap. So it's basically purely capacitive. That is, its value equal to a scale version via this scale of the actual cap that is in the circuit. So this way, by just a small cap that we put in the circuit in this feedback route, we can actually realize a much larger cap that its scale value is defined by this scalar, in which the RFET, this value, is the equivalent resistance that is observed between the drain. So if this here is drain and here is source of the JFET, between drain and source is a resistor that is RFET. And this RFET is its value, which is between, say, 25 ohm minimum, and it can go effectively or practically to infinity. So in this, this range of RFET is controlled by Vcontrol. So it's basically a VCR, or for this resistor between drain and source. So RFET or RDS is a function of the Vcontrol. By the Vcontrol, we can adjust its value, and its value is adjustable in this range. We refer to this kind of resistor as voltage control resistor, or VCR. Okay, if this circuit is working like this, what is the thing that we are effectively realizing is, because in the scalar in the formula of the cap, we have RFET that is controlled by voltage, we have realized effectively a Varactor. So a Varactor is a variable capacitor, which is normally implemented using diodes, a special type of diodes. But those have limited linearity ranges, and hopefully with this kind of circuit we have much more programmability in terms of the scale value of cap, and also a better, more linear behavior for the multiplied cap. So again, we are realizing a variable capacitor that is voltage controlled effectively, and this circuit is doing a capacitor multiplication. So from a small cap we can get to a much larger cap that is programmable. Okay, so with that in mind, I want to just mention that we get to minimum value of this JFET when the VGS, or the voltage that is as a result of this range of Vcontrol between maximum 0 and minimum -9 volt. So in that range, when Vcontrol that enables a value of VGS, when this VGS is effectively the highest, that is 0 volt, then we get the maximum current through the drain source, or basically just ID, of the JFET, which means the minimum resistance. So equivalent resistance becomes 25 ohm for the RDS or the RFET when the gate source voltage is 0. And when the gate source voltage gets to low enough value, let's say, as an example, say, I'm just making it up, some negative enough value, say -9, or somewhere between -5 and -9, depending on the choice of the JFET, then what happens is it completely turns off, ID becomes 0, and effectively that means infinite RFET. So that's how we are controlling the effective resistance of the JFET. The part number that is mentioned here is just the part number that is just mentioned here is just an example. This part number, it doesn't mean we have to use it. Just an example of a practical N-channel JFET that for example, can be used for this purpose. This is an N-channel JFET. Okay, so with that said, let me also show you the sort of a general response that we expect to see for JFET, for a properly considered JFET. So this is IV curve for JFET. If I can just show it here, there you go. So for IV curve of JFET, there you go. I hope that you can see it. So it's sort of what I just said. In the JFET, there you go. So in the JFET, we are not, this is the IDS as a function of VDS on x-axis, ID or the current of JFET, this current on the y-axis, and the VDS or the voltage between drain and source, VDS, is shown on the x-axis. We don't want to deal with the saturation region. That's not what we want. We want to deal with deep linear region here, the red circle that I'm highlighting. If we zoom in into that area, we get to this large circle in which you can see that the transistor, the N-channel JFET or Junction Field Effect Transistor is shown with the drain, gate, source. And then we are saying that when VGS is 0, which is the minimum value, maximum value we can consider, the line, current versus voltage line, has highest slope, which means lowest amount of resistance, like 25 ohm, 30 ohm. The moment we start reducing VGS to, say, negative 1.5, you can see that now slope is starting to decrease substantially. So effectively resistor RDS is now increasing because current is dropping. And as we do further, meaning that we get to negative 2.5, you see that the slope is further reduced, more resistance, and at negative 3, slope is substantially reduced. And if we keep decreasing VGS, this will becomes even less slope and more resistance, and at some point it will kill and shut down the transistor, effectively equivalent to infinite resistor. So with that said, we are just working in this region in a very small VDS range, which is good enough for us, and in deep linear region of the N-channel JFET. Okay, with that said, let me go back to the circuit so that we can run the analysis. So I'm going back to my circuit here. What is happening? So let me just remove or just shift this portion. We don't need to keep this here. I need to prove this formula, of course, that's my target, but for now I can put this aside. That's my target. Okay, so I just put the target there. All right. So what I'm doing is as simple as this. Since I need to find Z equivalent, remember that the best way to do that is apply test voltage between here and between ground or the AC ground. So V test is applied here. We apply a test voltage like this. As a result of applying a test voltage, a test current flow through the circuit. It will flow through the circuit. That test current cannot go through the input of ideal op-amp, assuming op-amp is properly biased, like 15 volt as an example, a negative 15 volt positive negative supplies. Op-amp 1 has proper negative feedback configuration. It's in linear region. Virtual short is valid for both op-amp 1 and op-amp 2. By that I mean the positive terminal and negative terminal, they have the same voltage, and that's virtual short. And also, as a part of being practically ideal, then the current of positive terminal input terminal and current of negative input terminal are 0. Nothing goes because practically the input impedance of ideal op-amp is infinite. So this current IT has to keep flowing through the cap. IT is equal to I cap. Reason I'm saying this is because what I'm trying to chase is I need to find Z equivalent via applying this test voltage. So this test voltage is what I know, is what I apply. What I need to find is what is the test current as a result of that. because the equivalent input impedance is V test divided by I test. This is known. I need to find this guy so that then I can find the answer to this question. So that's my target. All right, so a V test applied because of virtual short. That V test that appear at this terminal will also appear at negative terminal of the first op amp. And obviously for the first op amp, you can see that it is in non-inverting configuration. Basically what I'm trying to say is the first op amp looks like this. So I'm going to put it here. Like this. So you have positive terminal, V test, negative terminal, and for the bandwidth of operation, I assume we are in the whatever V test is applying is with the proper frequency, so it's within the bandwidth of the circuit. Within the bandwidth, the circuit just looks like this effectively. So this coupling cap becomes short, and as a result, we only have this nice thing. So whatever resistor we have here to Vcontrol, which is a DC, so we have two 1 meg, 1 meg, and to AC ground, which is our Vcontrol. Vcontrol AC wise is like nothing, so I don't care about it. And then the effective resistance of the FET is here. So equivalent resistance of the field effect transistor is here. That is controlled by the voltage that I apply as Vcontrol. And then we have the R feedback, which is the 25 kilo ohm. This is clearly what is referred to as the non-inverting configuration for the op amp. This VT, because of virtual short, appears here as well, negative terminal. And then for the practical range of RFET, just to show you, let's say that for practical range of RFET, it is much small. It is relatively smaller than 1 meg. Of course, for example, when RFET is in the range of 25 ohm, as I showed you. So see the range of RFET. I'm gonna show them again. This is the range of RFET. Starting from 25 ohm, obviously we can, when RFET is 25 ohm, which is the minimum of it, we can surely forget about the 2 meg in series here, in parallel here, and we can think of the gain of this circuit. So Vm at the output, which is this midpoint of the circuit, Vm, I can say Vm is equal to, it's a gain of non-inverting amplifier, 1 plus Rf divided by RFET, effectively, times Vtest, because all I did is this Vtest that appear at this node is right, and this Vm at the output. Between Vm and the Vtest is just a simple voltage division between all these two resistors that I'm showing, that as a result I get this sort of outcome. So effectively I can write a simple KCL here to solve this and get to this, which is well known. Okay, so and regarding this, let me shift it to here so that there is enough space for the rest of argument. I'm going to shift this to here, if you can see. Okay, great. So in this scenario, in this analysis, of course, RF is a fixed value, 25K. So in conclusion, Vm is 1 plus 25,000 or kilo ohm divided by RFET times Vtest. So let's keep that as our equation 1. I'm going to use it. Okay, we got to Vm. Now the next step is, of course, for op amp 2, the same thing. We have the positive negative supply voltage is properly applied. There is a negative feedback. Virtual short is there. Positive terminal is 0. And therefore, because of virtual short, negative terminal is 0 volt as well, effectively in virtual ground. It's a simple inverting amplifier. So inverting amplifier. And the inverting amplifier is well known by just writing a simple KCL here. All the current that goes through R2 should keep going through R1 because nothing can go through the input terminal of op amp. And if you do that, if I refer to output voltage Vout is simply minus R2 over R1 Vm, which is the input. Okay, let's refer to this as equation number 2. Great. So if I combine 1 and 2, of course, I get to the outcome that, so I'm going to use equation 2. And from 1, if I apply 2, I get VO, or Vout, is equal to negative R2 over R1 times 1 plus 25K divided by RFET, that's it, times, of course, times VT. So that is V over VT. So that is combined equation 1 and 2. You can refer to this as equation 3 so that I can use later. Okay, so one last thing. On top, here, we just talked about VT over IT as Z equivalent. Fact is, IT is equal to IC as we talked about it. Okay, so how can I find then IC or IT? Well, there is a voltage drop across this cap. That voltage drop is obviously, so there is a voltage drop across this cap. That voltage drop is obviously equal to voltage of the positive side of cap, which is just basically Vtest at the positive side. So we have Vtest here. And on the negative side of cap, we have Vout. So Vout here. So therefore, Vcap is just Vtest on positive side minus Vout. What I'm going to do is now, I'm going to apply, since I already computed in equation 3, as I showed you, Vout as a function of Vtest, I'm going to apply equation 3 on top. So equation 3 says this becomes Vtest minus Vout, as I showed you in equation 3 here, is just minus R2 over R1. So negative and negative cancel out the other negative, become positive. R2 over R1 times, as you can see, 1 plus 25K divided by RFET. 25K is 25,000. RFET times VT. Very nice. I can factor out VT, and but I can do it later as well. Doesn't matter. So let's refer to this, which I just computed VC, right? This is Vcap. So let's refer to this as equation 4. I am almost done because I can substitute equation 4 into, see the top left, I'm computing Z equivalent or input impedance as observed from perspective of Vtest. So in equation here, I need to just substitute for IT, which is basically just Vt over impedance of cap, and just be done with it. So I'm going to do it here. Okay, so I'm going to apply Z equivalent equal to Vtest over Itest, which is ICAP, and then applying equation 4, Vtest remains Vtest in numerator, but in denominator, Itest becomes Vtest, so Vc over, so IC is simply Vc over impedance of cap, which is 1 over Cs. So it becomes Cs times Vc, and then Vc from equation 4 is just 1 plus I factor that V test. Look at the equation 4. R2 on top, R2 divided by R1, 1 plus 25K divided by RFET, that's it, times VT. The nice thing is, this VT cancel out with this VT, and then we end up the equivalent impedance of this circuit. So if I change the color to, say, blue, equivalent impedance of this circuit is just 1 over S, because VT disappears, and times a scalar. So as a result, Z equivalent for input impedance is 1 over C times 1 plus R2 over R1 times 1 plus 25K divided by RFET S. So that's good enough to understand that, or to conclude that. Let me just say this. So this is good enough to conclude that we are done, because we just figured out that the equivalent impedance or input impedance observed from perspective of the input terminal VT is purely capacitive, because we have only 1 over S. See, we only have 1 over S, and then S is multiplied by some some value that is programmable, but it's just a value that is a scaled version of the original capacitor we have in the circuit. So effectively, we can say there is a total cap that is observed from the input impedance perspective, and it's purely capacitive, and the value of cap is this multiplied cap that is voltage controlled, because RFET is voltage controlled, that is here. Okay, I hope that this example is helpful in terms of showing how this circuit is operating, and how we are effectively realizing and implementing the sort of a Varactor or variable capacitor that is voltage controlled, as the formula here is indicating. I hope that this analysis is helpful. Thanks for watching.